My name is David Pankratz, and I'm going to be presenting our work, Vulkan Vision. So a bit of background before we dive in about what Vulkan is. Well, it's a graphics API, and the graphics API has the job of taking developer-provided data and programs and turning those into a highly efficient GPU hardware-accelerated executable that can render images very quickly. The user-provided programs are known as shaders, and they slot into graphics pipelines. So here I'm showing the rasterization pipeline, which has the vertex and fragment programmable shaders. The other stages of the pipeline are fixed function and added by the black box compiler. And typically those will be hardware accelerated to some extent. So in the rasterization pipeline, the input assembler, the rasterization stage, and the color blending stage are all fixed function. Now, conceptually, the rasterization pipeline is fairly easy to understand. There's a nice linear progression, so overall, it's pretty nice to work with. Now, for motivation for our work, let's contrast that with the ray tracing pipeline. So this was recently introduced into Vulkan, and this allows first-class support for the ray tracing algorithm. And I'm going to walk through exactly what the developer has to provide in terms of programmable shaders and what the driver adds through the compiler for fixed function stages. So the ray tracing pipeline begins with the ray generation stage, and this has the responsibility of creating new rays and beginning the tracing operation known as trace ray. Trace ray has a few jobs. The first one is to develop the set of candidate hits, and this does this by looping over all the possible candidate hits and checking them for validity. So the second job is, once you know all the candidate hits, determine which hit was the closest, if there is hits in the set, or if there are no hits, determining that there's a miss. The shader binding table is another layer of complexity. This allows indirect lookups for the shader to call for a given geometry instance. The net effect on the execution of the pipeline is that this acts as an indirect function call. So the next programmable stage is the intersection shader, and this allows developers to specify ray collisions with non-triangles. So for example, if you wanted a scene full of spheres, you would implement the intersection test in the intersection shader. The AnyHit shader is used to accept or ignore possible candidate hits, and this is often used for testing for transparency, for example, in the AnyHit shader. The other last two programmable shader stages are the closest hit stage and the miss stage. The closest hit is called once the trace ray operation has figured out the closest of all the hits, and the miss is called if there was no hit at all. And finally, the last level of complexity is that the closest hit and miss may invoke another trace ray call. So this is recursive operation. And the net effect of this whole complicated ray tracing pipeline is that the developer has to understand that there are loops, there's control flow, indirect function calls, and recursion, and try to figure out how their code will map to that and map to the hardware underneath it. So that's enough to make them a bit dizzy already. And as I mentioned before, this all happens in the black box. So the driver gets the shaders and then compiles them into a pipeline in addition to the fixed function stages. And then it gets even more complicated when you actually run it and you get to find out that there are silly dynamic interactions with certain geometries or something in your scene. And so this is enough to be very confusing at this point. So overall, the motivation here is that the ray tracing pipeline is very difficult to reason about. So our solution is to insert Vulkan Vision as a validation layer right above the black box and perform shader instrumentation to view into it. So before I dive into our approach, I will explain a bit more background, which is what are Vulkan validation layers. So Vulkan validation layers have the ostensible purpose of validating your code. So when you make a Vulkan API call, it will check that you're following best practices or that your code makes sense, like you've defined things before you've used them. But in practice, the interface for validation layers is really flexible. So developers have used it for things like the in-game overlays for Steam, for example, for performing frame captures to enable future replays of the frame, to take screenshots of the application, to monitor the FPS, along with many other purposes. So I'm trying to convey here that validation layers are very powerful and very flexible. And the mechanism that drives all of those different applications is that validation layers let you execute arbitrary code before and after any Vulkan call. So you're able to get a complete log of the application execution, and you're even able to therefore modify code before it reaches the driver. So now I'm going to walk through an example of how we use this validation layer interface in Vulkan Vision to do shader instrumentation and analysis of the subsequent data. So the whole process will begin when the application provides the shaders. So those will be intercepted by the validation layer. And then we have a instrumentation pass, which is programmable. That means that you can implement different instrumentation passes in this framework to get different kinds of data. So this will take the shaders, it will modify them, add instrumentation code, and then return that to the validation layer. And now the validation layer will pass those on to the driver. So if we take a step back, from the driver's perspective, it was getting the shaders from the application, and from the application's perspective, it was sending the shaders right to the driver. So this is another great feature of validation layers where it's entirely transparent. So you don't need any sort of application source code modification. It just slots in and everything works. So the driver will take the transformed shaders, turn those now into an instrumented binary, and that will go to the GPU to execute. So the GPU will execute it, produce some instrumentation data, and this will be fed back to our validation layer. So now we have some meta information about the execution of the binary that the Vulkan app was trying to create. And we will take this instrumentation data and provide it to the analysis module, which is also programmable. In addition to the runtime instrumentation data, we provide statically known data to the analysis module. Those are both consumed to produce a variety of outputs. So for example, inline commented shaders, heat maps, or simply standard out. And the operation of Vulkan Vision, such as which an instrumentation utility you would like to run, is controlled through the VK layer settings text file. So that was the overall flow of Vulkan Vision, and now I'm going to dive into a bit more detail about some of the primitives that we offer in the instrumentation pass and what problems they solve. So the first problem we need to tackle is how do you gather execution data from the ray tracing pipeline? So we offer two primitives for this purpose. The first one is the thread update primitive. So this primitive operates by writing an arbitrarily specified amount of data to the instrumentation buffer for every thread that executes it. And then the second primitive, warp update, is the same, but just writes whatever data was specified per warp instead of per thread. So these are very flexible primitives that allow you to write whatever data you want for that given instrumentation pass you wish to develop. And the way it transfers data looks something like this. So if you added warp update to every shader, then you would see that the instrumentation buffer would be populated with the execution data. So for example, if you put warp update in every basic block, you would get data from every basic block execution. So this is good. It gives you enough data to actually get a complete trace of each shader's execution, but we still don't really have a view into the trace ray called black box. So to do that, we need to be able to track the warp execution between shaders, not just track it within a shader. So that's the next problem we need to solve. To do that, we come up with the notion of a unique warp ID, and the primitive that creates that is the create warp ID primitive. So now we add that in addition to the warp update primitives to our pipeline at the beginning of the ray generation shader. And the way this operates is all threads that execute create warp ID will decide on ID for the warp that they belong to, and then write their ID and that agreed upon ID to the instrumentation buffer. So this is sufficient data to construct a mapping from the thread ID to the warp ID. And then thereafter, in every warp update call, we include the thread ID, and that lets us figure out exactly how warps went from executing one shader to another. So now we have a trace of warps executing the entire pipeline, in addition to the trace of warps executing all the shaders. So this is actually enough for a complete view of the execution of the ray tracing pipeline. So that's really exciting. But then we need another solution to the problem that This is still inefficient, so the default instrumentation is writing a lot of statically known data to the buffer, such as the shader the data originated from, how many words were written, stuff like that. So that's where the fourth primitive comes in, the instrumentation call site ID. This primitive lets you relate statically known data to runtime produced data, and I'll dive into exactly how that works. So on the left, I'm showing the instrumentation buffer, and this buffer is full of buffer entries, and each buffer entry is composed of the instrumentation call site ID, the work item ID, also known as the thread ID, and then the payload. And the payload is defined by the particular analysis that creates the buffer entries. So you'll see that the buffer gets filled up with a bunch of these buffer entries. And then if we go to the static side, so the data produced at compile time, it also has an instrumentation call site ID, as well as additional metadata, such as the type, payload size, and you could optionally include stuff like the shader ID that it belongs to. So of course, when you're now parsing the runtime buffer, you can look up the static data based on the instrumentation call site ID, and now you just saved having to include the type, payload size, shader ID all in the runtime buffer. Additionally, you can transfer larger bits of data, such as the control flow graph or the instructions that belong to each basic block for more advanced analyses. So this instrumentation call set ID gives us efficient buffer utilization. So in aggregate, our instrumentation pass solves a number of key problems in understanding the execution of the ray tracing pipeline and doing so in a very efficient way. So that's the high-level operation of Vulkan Vision, a bit more details about our instrumentation pass. So now I'm going to get into some of the results, or more particularly, what kind of questions can we now answer because we have Vulkan Vision. So the first one is a developer who might be wondering, how do they optimize their ray tracing application? Well, we have a few different things that we can provide them with. So the first one is hotness information. So hotness is the runtime execution count of each instruction. And we show here two graphs from different ray tracing applications with the hotness information on the y-axis and the instruction or pipeline PC on the x-axis. So the middle graph shows a fairly normal looking graph where there aren't too many tall peaks or things that absolutely dominate the runtime execution count. However, if we contrast that with the pipeline shown at the bottom, I just highlighted in red the part of the pipeline that does absolutely dominate the dynamic execution count. And this is the prime example of something you would pass along to the developer, telling them that they should look for optimizations in this part of their pipeline. The same data can be presented inline in the shaders themselves. So here, these two comments are automatically generated by Vulkan Vision, and the call sites of the instrumentation that generated this data is immediately below both of the comments. And this tells you the dynamic hotness or the dynamic thread executions, and it also tells you the SIMT efficiency. This is a measure of the hardware utilization, and it's calculated by taking the average number of active threads for each runtime execution of the basic block. So we can actually deduce from this little code snippet that this if statement has a negative impact on the SIMT efficiency for a non-trivial number of the thread executions. For example, there's roughly 2,600 within the if statement and 8,600 outside of it. So this gives the developer enough information to reason about the hotness and the efficiency, and together that lets them make pretty informed decisions about what they want to optimize. And presenting it inline in the code itself makes it very productive to relate this knowledge to the original pipeline. So next, we've helped developers understand their binaries, but now how do we help them understand the dynamic factors like the geometry that actually has a non-trivial impact on the runtime execution? Well, the first thing we can give them is the thread execution time heat map. So in the bottom left, this heat map is automatically generated by Vulkan Vision. And the way it works is that each pixel receives a color based on the thread execution time. So this is calculated using the SPIR-V KHR shader clock extension, which essentially asks the GPU for a hardware performance counter indicating how many cycles it takes to compute that thread's amount of work. So we convert that to a color, we assign it per pixel, and we end up with the image in the bottom left. And I'm showing the original application in the bottom right. And what's really interesting is we don't generate the heat map with any knowledge of that image in the bottom right, and yet we can see a clear correspondence in the data. And not only that, we can also let the developer use this data to make informed decisions about whether certain materials or effects are expensive and if that's giving them their desired bang for their buck in terms of visual quality. So this is another example of very actionable feedback that we provide to developers. Another interesting study is if we hold the application and the ray tracing algorithm constant, and we just alter the geometry, what effect does this have on the dynamic execution of the ray tracing pipeline? So I'm showing two graphs here from the hairball geometry and the Sponza geometry for the same ray tracing application. And the graphs show the distribution of warp path lengths. And warp path length is simply how many basic blocks were executed by a warp, and then we accumulate those for all warps to generate these graphs. So this peak in the graph, which shows the highest number of warps with a given path length, corresponds to the maximum ray bounce limit in the application. And since it's the same application, we see the same peak in both geometries, but we see a difference here where Sponza has no short warp path lengths, but hairball has a reasonable number. So we might ask, what causes this difference? What about these geometries is influencing the dynamic execution of the ray tracing pipeline so much? So these are the applications, the geometries hairball and Sponza. So we can answer the question I just asked with heat maps again. So if we convert those to heat maps, now we're seeing the dynamic execution of the ray tracing pipeline presented as colors. And the green here corresponds to few bounces. So essentially this is saying that the rays that hit these outward strands on the hairball end up bouncing and missing, and then those warps have no more work to do, and then that's a short warp path length. However, if we look at Sponza, it's almost entirely sort of this red, more blue or purple color, which corresponds to the maximum number of bounces. So if you remember, I showed that peak in both graphs, and as we can see, that corresponds to these purple regions in both graphs. However, we were asking the question, why doesn't Sponza have any short path lengths? And we can see that's because there are no green areas because rays get trapped into the maximum number of bounces. So using the vVision output, we can help developers understand the dynamic factors such as scene configuration or geometry on the complex ray tracing pipeline. And we can also help driver designers or hardware developers figure out how to design their next iteration of hardware drivers using Vulkan vision. So for example, we did a characterization study where we looked at all the ray tracing pipeline executions for a number of Vulkan ray tracing applications, and we studied the SIMT efficiency metric I mentioned before. So this is again sort of a proxy measure of the hardware utilization efficiency. So the applications I just highlighted use random sampling. So you sample with randomly generated rays and try to converge to the correct color. However, this effect, although it produces good visual effects, is utilizing the hardware fairly poorly. So this is a vector to look to optimize how you can achieve this same random sampling effect with better hardware utilization, such as the bars that I'm showing that don't do random sampling. They achieve much better hardware utilization. We also did a compiler study specifically for the NVIDIA compiler. So this is an example of how we can kind of gaze into the black box, since we don't really know what's going on, but we can still deduce some information about it. So in particular, we're looking at speculative reconvergence, which leverages the independent thread scheduling hardware behavior. So to explain that, independent thread scheduling means each thread in a warp has its own program counter. So essentially, it can sort of be in two places at once a warp can be in two places at once in the ray tracing pipeline. And speculative reconvergence means that those threads can reconverge after diverging a bit. So a concrete example of what this lets you do is have threads on different iterations of a loop executing the same code in lockstep, which wasn't possible before independent thread scheduling. However, what we're looking at in this figure is what kind of impact does this have on the ray tracing pipeline? In particular, how much divergence does this feature cause? So a way to measure this is looking at the number of ray generation entry executions versus the exits. So assuming a traditional lockstep execution, this would be 1-to-1, but in independent thread scheduling architectures, we see that it gets as bad as 12 times as many ray generation exits as entry point warp executions. So this means that on average, 2 to 3 threads are active when the exit is executed, which is a very poor SMT efficiency. So I think this was a very interesting study where we were able to gaze into this black box compiler and sort of deduce interesting behavior that was occurring. We also looked at the hypothetical hardware change, which is thread compaction. So what thread compaction refers to is rearranging threads in a set of warps before continuing execution. So specifically, we looked at immediately before trace ray calls, which are very expensive. And we looked at how many executions of those calls could we save by rearranging the threads between warps. And so we studied this for all the ray tracing applications, and we also looked at different compaction window sizes, or how many warps do we rearrange threads between before continuing execution. So we can see a nice difference in behavior depending on the application and other dynamic factors like scene configuration, which actually have a large impact on how effective this hardware change would be. So the motivation for this is it lets you get very concrete data before you go to the effort of trying to run this in the simulator, which would be time consuming and expensive to implement. There are some considerations. Despite being able to answer all these interesting questions, there are some questions we can't answer. So in particular, shader instrumentation cannot gather all black box details. We showed an example of somewhere we can, but others like register allocation, which is very architecture specific, we can't really do. And you would have to add some sort of instrumentation in your black box compiler to be able to study this. However, the benefit of doing shader instrumentation is that it's vendor agnostic, so we aren't bound to a single GPU vendor for our studies. Another consideration is that shader instrumentation may affect and is very likely to affect the downstream compiler's optimization passes. And despite this, we were able to demonstrate that it does produce very useful and actionable results, such as that heat map I showed you before, where the heat map looked very close to the final rendered image without any knowledge of the final rendered image. So clearly it's producing accurate and actionable results. So that's all I wanted to talk about. Thank you for listening this far. In summary, our tool Vulkan Vision facilitates profiling of Vulkan applications, enhanced debugging of Vulkan applications, and it enables very interesting limit studies of the application, the compiler, and potentially the hardware that the Vulkan application is executing on. And in particular, we provide a very interesting view into the driver and hardware black box that previously was inscrutable to developers. So thank you very much again. If you wish to contact any of the authors, these are our addresses. vVision is open under the Mind Insight project, and thank you very much.